Hello, hello. Namaskar. A very good morning to everybody. On behalf of the seminar committee, I, Shobhan Majumdar, welcome one and all to today's Foundation Day function. I'm sure many of you might know that on 19 February 1984, the then President of India, Gyani Jail Singh, laid the foundation stone of our center. Today we are celebrating the 40th Foundation Day of our center. We are extremely honored to have with us today Sri Kamlesh Nilkanth Vyas, Chairman Atomic Energy Commission and Secretary, Department of Atomic Energy, Government of India, as the honorable chief guest of today's function. A hearty welcome to you, sir, at RRCAT. We are also honored to have with us today Dr. Kamachi Uthandi Mudali, Vice Chancellor, Vellore Institute of Technology, Bhopal, and former Chief Executive and Chairman of Heavy Water Board, a flagship industrial unit of Department of Atomic Energy, as the honorable guest of honor of today's function. A hearty welcome to you, sir, at RRCAT. I would also take the privilege to welcome the team of colleagues from Indira Gandhi Atomic Center, Kalpakkam, who have come all the way from Kalpakkam to attend this function prior to attending the IGCAR RRCAT collaborative meeting. We are also extremely honored to have many eminent personalities with us in today's program. I extend my warm greetings to Professor Amlan Pal, Director UGCDAE Consortium for Scientific Research, Professor Basant Sathe, Center Director UGCDAE Consortium for Scientific Research, Indore, various Vice Chancellors of various universities, Professor Patnaik, Professor Prithviraj, Professor Ganeshan, also Dev Kumar Basudevan, an eminent personality of MOU, various eminent doctors, Dr. Pankaj Parashar. I also welcome other respected professors from different institutes, Professor Sharad Gupta and other professors from IIT Indore and DAVV, high-ranking officials of Indore District Administration and Police Department, and also the personnel from press who are present here today. We are extremely delighted to have with us the industry partners who have come to attend today's function. I extend my warm welcome to each one of them. My cordial welcome to all the former directors present here, Dr. P.D. Gupta, Dr. P.K. Gupta, Sri Satish Joshi, and former group directors, Dr. Anil Rawat, and all other attendees present online for today's function. I also welcome all my senior and junior colleagues and the friends and the students for being here with us at this proud moment. Thank you all for sparing your valuable time and accepting our invitation. Now to begin the ceremony, I would request our Honorable Chief Guest, Sri K.N. Vyas sir, to kindly come on the stage and take seat on the dais. I request our Director, Dr. S.B. Nakhe, to please escort the Chief Guest onto the dais. I also request the Honorable Chief Guest of Honor, Professor Kamachi Mudali, to please come on the stage and take seat on the dais. I request Sri Purushottam Srivastava, Director, Proton Accelerator Group, to please accompany Professor Mudali onto the stage. Thank you, sirs. To proceed further, I would request Dr. S.B. Nakhe, Director, RRCAT, to welcome the Honorable Chief Guest with a flower bouquet. Thank you, sirs. Now I request Sri Purushottam Srivastava, Director, Proton Accelerator Group, to welcome the Honorable Guest of Honor with a flower bouquet. Thank you, sir. No auspicious occasion can well begin without the invocation of the Almighty. So before we proceed, I would like to request all the dignitaries on dais to come for the worshipping of Devi Saraswati, the goddess of knowledge and wisdom, and lighting of the lamp. Thank you, sirs. As you all know, RRCAT was established by the Department of Atomic Energy India to carry out research and development in two frontline areas of science and technology, namely lasers and particle accelerators. On February 19, 1984, the then President of India, Gyani Jail Singh, laid the foundation stone of the center. In June 1986, the first batch of scientists from Bhabha Atomic Research Center, Mumbai, moved to RRCAT and scientific activities were started. Since then, the center has rapidly grown into a premier institute for research and development in the areas of lasers, accelerators, and their applications. So today we are celebrating the 40th Foundation Day of RRCAT. I feel delighted to share with you that the proceedings of today's function are being transmitted online in different lecture halls and auditoriums within RRCAT campus and also in the other Department of Atomic Energy units through YouTube. These arrangements has been done so that those colleagues of ours who are not here in person in this auditorium can attend the function online from their respective places. Now, as per the tradition of the Foundation Day celebration of our center, Director RRCAT gives a brief account of the activities and achievements of the center during the past year. So now I request Dr. Nakhe, Director RRCAT, to please come onto the podium and present the RRCAT annual report for the past year. I request the dignitaries on dais to please take their seats in the audience.
Yeah. Shri K. N. Vyas, Chairman Atomic Energy Commission and Secretary Department of Atomic Energy. Professor Kamachi Murli, Vice Chancellor VIT Bhopal Campus. Professor Amlan Pal, Director UGC DICSR. Other dignitaries, former directors of RRCAT, invited guests, members from press, members from industry, my colleagues and students. Very warm welcome to all of you to this Foundation Day function of RRCAT. And as a tradition, I'll be presenting a brief account of major achievements of our center that has been done with hard work of all the colleagues here. And the credit goes to all the colleagues here for these contributions that I'm going to present. So this is a day also to remember the contributions of Dr. Raja Ramanna, who has taken keen interest in founding and nurturing this center, particularly in initial days. And with his blessings, we are progressing further. So I pay tribute to him and recall his contributions and will proceed further with the contributions of our center. I'll be presenting mostly the contributions of last 1 year, but however, for the benefit of those who are not very much familiar to the activities of center, I'll give some background wherever it is required. So I'll be proceeding on these points, a brief historical background of the center, then achievements of accelerator program, laser program, and technology development, HRD, outreach, and incubation activities, mainly that are all related to the scientific and technological developments of the center. So as informed earlier, our center was formed, or the foundation stone was laid on 19 February 1984. At that time also, Dr. Raja Ramanna was present here, and this was a barren land at that time. And subsequently, on December 17, 2005, then Prime Minister Dr. Manmohan Singh renamed the center in the memory of Raja Ramanna. So since then, our center is known as Raja Ramanna Center for Advanced Technology. And we had major mandates, as indicated earlier, on laser program and particle accelerator program. So coming to the particle accelerator program, so we had electron accelerators like Indus 1 and Indus 2, electron LINAC, and free electron laser activity. We are developing proton accelerator program also, and at present major contributions are going to the Fermilab collaboration, and there are many related technologies that are required for this particle accelerator program. So I'll review mainly those. So this Indus 2 or Indus complex is our flagship project of the center. As you know, the electrons start from here, which is a microtron. Then we have a booster synchrotron where we accelerate these electrons, which are generated at around 20 MeV to 450 MeV or 550 MeV. And then we have two storage rings. One is Indus 1, where we are going to 450 MeV at 125 milliamps, or Indus 2, which is the 2.5 GeV machine with 200 milliamps current. This is our main workhorse right now. All the beam lines on Indus 1 are there in place. There are 7 beam lines on this. And on Indus 2, there is a provision of 26 beam lines. And right now we had 18 beam lines commissioned on this, and work on remaining beam lines is going on. This year, we have completed this BL20 beam line, which is this X-ray magnetic circular dichroism beam line, which is a very special beam line. I will describe it later. And I'm happy that today our chairman will be formally inaugurating this beam line when he will visit the Indus complex. And I'm also happy to announce that this VL26 beamline construction and commissioning project is approved. And this design is worked out by UGC-DAE CSR. And this is a close collaborative project with UGC-DAE CSR. And I hope this project will be completed in time in coming 3 years. So coming to the Indus utilization, we had fantastic utilization this year. So we had the highest number of working hours for users on the Indus 2 in this year, that is 2022. We have clocked 5601 hours, which is higher than any of the earlier years. These two are definitely low because of the COVID, but this year we had done very good. And total availability was also good. We had a 339 days available for round the clock operation for these Indus accelerators. And Indus 2 has given another feat, that is 65 hours of continuous operation on single charge of the beam. So now we are very confident on Indus operation, and looking forward to handle next generation projects of synchrotron. This is all possible because of our training and licensing program. I'm very happy to announce again that DI has recognized these efforts, and this Indus operation staff has been granted the qualification incentive scheme. They're under that scheme now. So our reliable operation of the Indus machine is recognized at departmental level. And continuing on these efforts, we have taken up the TQL program, that is Training, Qualification and Licensing program for our staff in July 2022. 43 staff members are now being trained for this, and they will be deployed for staff duty soon. Now coming to what is the impact of Indus utilization. So last year we had 991 user experiments that are carried out. Again, those are higher than any of the earlier period. And 177 publications have come out. Although this number is lower than last 2 years, but probably the researchers are more busy in doing the experiments than as compared to last 2 years, where because of COVID period, they're more active on publishing the papers. But I'm sure this number of papers will go subsequently also. More importantly, several Indian industries, particularly pharma industries, they have now started utilizing Indus beamlines, and the results are, and its utilization is quite obvious and clear that, sorry, these two applications filed recently by Indian pharmaceutical companies in FDA USA, they require certain data, and that has been generated on Indus 2 beamlines. So our now this Indus machine has started showing its industrial impact in the market, or say in the industry level. Moreover, there are NDA, that is the non-disclosure agreement, which is very important to have industry on board, has been signed, because many industries require different form of NDAs, and now we have made it clear and through from our department also, that is the through legal cell. So industries can now come with more confidence, and it can be utilized. So as said earlier, this is the beamline that we have completed this year, and it is ready for user operation now. It will be formally inaugurated today. This is a very special beamline because one thing, it is on undulator, so which is a very specialized device. So this is the second undulator on which we are going to use this beamline. Moreover, it has a circular polarization control also, and there is a energy range from 300 eV to 1000 eV in circular polarization control, and in linear polarization it is from 300 eV to 2 kV. So this has a in-house developed magnet that is deployed on this beamline instrumentation. So this gives additional confidence on developing indigenous components and systems for beamlines. I'm sure this will help us to take up the next generation synchrotron projects in a better way. So these are some of the trial results on this XMCD beamline, where this nickel LH are identified at 2 different levels. We are upgrading already installed beamlines also, and trying to improve their performance wherever possible. So this is BL16, on which this vacuum compatible X-ray fluorescence setup is used, and this total reflection XRF set is also installed here. This has enhanced the sensitivity of detection of low Z elements considerably as compared to earlier results, and concentrations of all elements are 10 ppm at this level. This was the earlier results, but now with this addition of these setups, XRF and TXRF, we are getting much more clarity and enhanced sensitivity in identifying these peaks. There are other developments also. This engineering application beamline is a unique beamline where we handle industrial samples for stress analysis, and this is very important for our DAE projects also, on which we have now installed machine vision based automatic sampling alignment system and post-focus mirror alignment system on this. With these systems in place, now the data acquisition will be much faster. Moreover, a fully automatic sample alignment system is also installed on BL12, that is ADXRD beamline. So with this, now the dependency on very specific persons will be eliminated, and the data generation can be much faster. So these are some of the additions on the improvements on beamlines. We are also upgrading Indus 1 also wherever there is a need. So this online synchrotron light monitor has been installed here, and this is a very useful device because it gives a proper alignment of these beams continuously. And we have another fluorescent screen monitor is also developed, and it can be used for very precise alignment of the Indus beamline, Indus 1 beamline. Apart from this beamline instrumentation, as stated earlier, there are various other related technologies like control electronics, software, magnet, power supplies. On all these fronts, we are upgrading our systems. One of this is VME bus location monitor. This has been developed, and its applications are finding sequence accessed monitored locations, and then measuring various software parameters on the control systems. And total 31 timestamps are stored in the memory for each monitored location, and this will give a much better performance because here the resolution is of order of 3 microseconds. So this is a excellent system, and I'm sure again that this will enable us to take the next generation synchrotron sources with much more confidence. This is a multi-channel programmable trigger generator. When there are so many systems to be operated with precision synchronization, such type of precision programmable trigger generator is required. And this has been completed and installed. This is now being utilized for LINEAC and scan magnet power supplies for synchronized operation. As you know, Indus is a very big system, and thousands of parameters are acquired per second. And operator's job is very critical there, and he has to take care of operating crew rather has to take care of number of other events and incidences going on there. So to ease out that job, a single button operation of Indus 2 is proposed, and its initial trials are taken up, and it has been implemented successfully. Now will be going on slowly for its deployment on the full system in time to come. But this monitors number of parameters, and it gives a very reliable operation. Because of this automated operation, the beam field life time will be reduced, so the availability of the machine will be increased, and it gives a sort of AI-based or say machine learning-based technique, so that the feeling of beam and system monitoring will be much more convenient and fast. So there will not be chance of error in that case, and nothing will be left to the personal judgment there. Coming to the magnet technology, this is a undulator, planar permanent magnet undulator is developed. This is developed in the magnet technology development division here. And this is a use for undulator. This is a 2.5 meter long aluminum jaws are there, and this is a 500 millimeter long NDFEB magnet based permanent magnet based system, and this will be used for our further undulators. Coming to the power supplies, a very special power converter for superconducting magnet is developed. This is at 10 volts, 1000 ampere, and its stability is around 500 plus minus 500 ppm. This uses very novel converter layout technologies, and it has a staggered thermal cooling also. So this will be used for testing superconducting wavelength shifters that are being developed on Indus 2 SRS. So this is a very useful power supply. On the vacuum front, two new techniques are developed. One is a hybrid UHV pump, which utilizes sputter ion pump as well as the NEG pump. So both are operating there simultaneously, and there are different pumping speeds with two different technologies. And the main advantage is here is we can reach ultimate vacuum of in the range of 10 raised to minus 11 millibar. And this is another sputter ion pump, which is a lightweight sputter ion pump. This is because of the housing is changed from stainless steel to aluminum based. And here, being lighter, and there will be different material used, there will be low induced activity. This is important point when we are using these pumps in a radiation environment. And here also the ultimate pressure is 10 raised to minus 10 millibar, which is quite good for this type of applications. So apart from operating very large vacuum systems and maintaining them continuously, these are the developments on the vacuum technology as such. Now coming to the another important electron beam accelerator facility, that is the E-LINEAC. This slide is well known, and I had shown it even last year, because this is the facility layout that we are having at the ARPF, which is 5 kilometers away from here. This system is operating very well, and it has been now offered under incubation center through various industries to get their products irradiated. So I'm very happy that in last couple of months, multinational company like Becton Dickinson, they had come and got their product irradiated here by paying the charges that we are decided. So now we are maturing to utilize this facility for the benefit of Indian industry, and it's ripening its benefit subsequently for the development of the country. So here the radiation source is 10 MeV electron linear, 6 kilowatt, and it is capable of operating in like industrial environment. This is the, we had ARB licenses for this, FDA license, and all ISO licenses for this, and we can sterilize class B medical devices in this facility. Then we had processed so many type of products, medical products here, and there is a continuous growing demand on this. This is a just highlight of different type of products that are developed on this. And since this Becton Dickinson is an international company, they now carry on their product even the name of RRCAT facility where those are irradiated. So RRCAT now name is now going everywhere. It will be, it is heartening to know that earlier this company was transporting these devices from Haryana to Indonesia to get this irradiated. Now they are bringing to RRCAT ARPF facility, and they need not have to send overseas for this purpose. So this is E-Linac is for industrial or say medical sterilization, but definitely one application in mind is for the food irradiation. Once we go for food irradiation, there is a need to control the highest electron energy that is coming out of the beam, and that limit has to be less than 10 MeV. So we have developed a limiting device that is limiting the electron energy at 9.5 MeV through a 270 degrees magnets here, and with this we can operate the system for food irradiation purpose. Now this system has been operated for a continuous 32 hours of operation with a pretty stable beam energy and power and current. So now we are confident that we can utilize this device for food irradiation purpose in time to come. This is yet another electron accelerator based facility. This is a, in fact, combination of laser and accelerator facility. This is a free electron laser facility that is working here. This is installed in 60-meter long and 5-meter wide tunnel, and we have achieved 12 to 40 micron tunability of the wavelength, and this is a unique facility in India that is operating here. Now we have, in this year, we have made it available to the users. Earlier, we were developing this and trying to optimize it and gain confidence on its reliable operation. Now this has been made available for users, and there are number of other experimental setups available so that samples can be tested on this. This is particularly useful for material studies in the superconducting applications and other magnetic applications. So we have time domain and frequency domain analyzers and many other systems that are available here for utilizing this facility. Again, to take this utilization to the next level, we have, and enhancing this technology, we have adopted this wire-writer photography setup for microscience patterning, and we are now going ahead with another facility that is the terahertz FEL, which will be installing or developing in the near future. Coming to the proton accelerator, a lot of theoretical studies are going on, design studies are going on this. So this is development of indigenous codes for proton accelerator. As such, the center has a very ambitious project of going to 1 GeV pulse proton accelerator in years to come. But we know it is a very ambitious project, and we have to pass through different stages for that. And preparation starts from these basic designs. So we may go for something like in between proton synchrotron of 270 MeV energy in between, and then scale up to the further levels. But these theoretical studies are very important, and we are gaining confidence on design of this. Apart from theoretical studies, there is a lot of fabrication techniques and very precision fabrications are required, like this radio frequency quadrupole. These are very important devices in going to the proton accelerator, which requires machining of coppers with very fine, like profile accuracy of less than 20 micron and surface finish of 0.4 micron. So these are very precision fabrications, and fabricating one full structure takes maybe a couple of months also, and even a single error will make the piece unusable subsequently. So we are developing the capabilities on infrastructure and as well as the expertise of the manpower. So we are developing this confidence, and this RFQ structure is uh, developed, and this first segment is completed with this. There are similar other devices also that is required. One is this proton beam dump is required for this 3 MeV machine also. And we have developed special technique of electro deposition of copper on aluminum mandrel, and then subsequent machining to achieve this desired properties here. So this is a very unique device that has been produced in our workshops at RRCAT. So apart from that, we are going for the RF characterization and tuning of the RFQ at 325 megahertz frequency. This is the before tuning of axis deviation here. And once we go for a fine tuning with the field profile, gets tuned within plus minus 4% of this. So we are getting confidence in developing this RFQ and its final deployment. Going to the further on proton accelerators, we are contributing to the fabrication of the cavities, superconducting RF cavities. But before I go to those details, I would like to show the end result, that is a 5-cell high beta, that is beta is equal to 0.9 to 650 megahertz RF cavities that are fabricated at RRCAT have been successfully integrated into the cryo module at Fermilab, and they have declared it, and it is a grand success for RRCAT's contribution so far that has gone into the superconducting RF cavity fabrication and all related technologies. So in this direction, now I'll show what we are doing in this case, because that is the end use and application. And we have installed a clean room here. This is a very high-end clean room, ISO 4 class clean room facility, wherein we need to process these RF cavities. And it requires many processes. One of that is high pressure rinsing by using ultra pure water. So this ultra pure water generation plant is also installed, and high pressure rinsing cavity facility is also installed. So now we are ready with all these facilities, and we can take up the RF cavity fabrication as desired and as required for the subsequent programs of the Fermilab collaboration, as well as we are trying to use the same cavity for our own programs in time to come. So apart from those minor finishing of the cavities, we had all the facility right from starting from the sheet to all fabrication and further processing, electron beam welding, and we are getting into the studies of this because there is a idea that we can go for nitrogen doping also, and it will improve the performance at the cavity. Of course, it is a study part as on date, but we are able to carry out these studies and doping studies at RRCAT. These RF cavities needs power supplies also, and for Fermilab, we are supplying this 650 megahertz RF power supplies based on solid state amplifiers. This is again a unique development at RRCAT, and 40 megawatt average power supply has been developed and sent to Fermilab, and it has been tested there. More than 1500 hours of operation has been completed with this, and probably will get we'll have the responsibility to supply many such power supplies in future to Fermilab, because this will be a major in-kind contribution from our country. Of course, this will be produced by our industry partners, either at ECIL or any private industry subsequently, but the design and final responsibility lies with RRCAT. And now we are confident that we can do that job very efficiently. Now coming to the other program, that is the laser program, and it covers lasers, photonics, and other materials also. So I'll briefly cover on this laser systems, photonics materials, and other associated technologies. We have developed a underwater laser cutting technology for removing cobalt bundle that is to be loaded in time to come into the standard fuel bundle of our nuclear power reactors. This is required because there is a demand for cobalt 60 sources, and right now the whatever the sources are available that are not enough to fulfill all our demand. And if we are very capable and efficient in doing that, there is a lot of export potential also for this. And to do that, an important step is to take out this central bundle here, which will be a cobalt in the fuel bundle that has to be taken out after a certain amount of exposure into the nuclear power reactor. And this has to be done underwater cutting with a remote control. So it requires a laser-based control system, cutting and processing system. So RRCAT has taken up this development, and its prototype has been demonstrated successfully. And in time to come, we'll robotize it and utilize it wherever there is a need to deploy such type of system. We are developing different type of lasers, and there is a ever increasing demand for higher power, higher efficiency, and going to this. So earlier we had gone up to 1 kilowatt. Now we are at 1.5 kilowatt average power and 30 kilowatt peak power with long pulse operation, and the pulse width can be controlled also. So we can go for proper welding and cutting applications using this laser system. So this is tested, and it has a ceramic reflector pump chambers, which is again a novel design, which will provide a long-term reliable operation for this system. And it has a single U-shaped laser resonator, so which will provide ease of alignment also. So this is the system that we have developed, and it is demonstrated for cutting more than 40 mm thickness of SS and welding 8 mm SS thickness. Earlier we were up to around 32 mm thickness was possible, but now we had gone one step ahead in this direction. We have developed a very specialized system for welding PFBR fuel pins, and earlier we have provided one laser unit, and it has tested successfully in the field. So now with the confidence generated and feedback received, we had gone for a next generation system with two such systems are developed, and this will be deployed for welding of PFBR fuel pins that are required for our fast breeder reactor program. We are contributing to the LIGO project also. We are a partner to Laser Interferometric Gravitational Wave Observatory program, and we are making our capacity building ready. One of this is to have an ultra stable laser and with high power in that direction. So it requires a very stable laser in a sort of monolithic construction and non-planar ring oscillator. So this has been developed, which is delivering more than 20 watt of power at 1064. So this has a better than 0.1% stability over 24 hours, and this system is now ready, and we'll be deploying it for a 10-meter prototype interferometer that we are developing here to have experience on to gain experience on operating and controlling the long interferometer that is required for the LIGO project. Another important activity is laser additive manufacturing. This is a very new technique that is coming up and very popular and finding niche application in certain areas. It is very useful in generating very specialized joining techniques also, say like joining two dissimilar metals, etc. In addition to the very specialized microfabrication. So we have developed laser additive manufacturing systems in CAT on both the technologies, that is the powder fusion bed and direct energy deposition. This system that is shown here is a 2 kilowatt laser based LAMP-DD system, and this is ready for transfer to BRC because this is now fully operational here. Earlier we used to get a lot of demand from BRC for doing certain parts. Now it is decided that we'll have the system installed at BRC itself, so the turnaround time can be reduced. And of course, we'll have more experience on deploying this system at user end. So BRC people have come and had an initial inspection and training also on this system, and this will be given to BRC soon. So we have produced very specialized bushes and components on this. That is the tungsten carbide clad deposition on SS304. This is a very specialized fabrication that we have done, and 600 numbers are supplied and 3,000 more are to be supplied in near future. We have gone for very specialized fabrications like conforming cooling channel die. These are required for industry, mold industry particularly, and this has been successfully demonstrated. I'm happy to announce here that this system has been put for incubation, and today, later on this, after my talk, we'll be handing over this incubation agreements with the industry on today's function itself. So there is a lot of interest in these machines in the industry, and I'm sure we'll be developing and marching ahead with this cutting edge technology. RRCAT is developing and supplying lasers for various specific BRC laser projects requirements, because we need not duplicate the work and expertise. So RRCAT has expertise in developing lasers, and BRC is utilizing this very effectively in their isotope separation program. So this is a 40-watt solid state laser that has been developed for BRC, and it will be used in their ongoing medical isotope separation program. We are using lasers for advanced techniques also. This is a magneto-optic trap based system for detection of G, that is the gravitational constant. And this is a very advanced system. It's a sort of quantum metrology, and where we can measure the G factor, that is the gravitational constant, to this accuracy, that is the 5 digits and 0.3 later on. So this will be useful in mining applications and many other applications subsequently. Of course, it is a long way to go, but this initial demonstration has been done. Of course, the system is quite bulky at this stage, and it is based on the cold atom quantum and atom interferometry subsequently carried out on this setup, which, because the atom interferometry signals are dependent on the local gravitational constant there, and that can be measured very precisely using this system, and this we can deploy subsequently. Coming to now the material science activities specifically. Of course, this is an activity for laser application, but it has been done basically for material science development applications. This is for bonding and packaging of laser diode. This was a very crucial area where we were lacking earlier, and thanks to Corona period and the ban on Chinese products during that period, because earlier these industries, they were sending these modules back to China and getting the new one repaired from there or replaced from there. But once that was stopped, then they came here looking forward for solution. And our scientists put a lot of efforts in identifying what has been going wrong, where we are lacking in our earlier efforts. And being synchrotron on this campus, that was an additional advantage. We could go and identify precisely the materials and what is the requirement. And with hard efforts, subsequently we developed this technology where we can now bind these laser diode chips to these are arrays to the heat exchangers below, that is the copper structure there. And now the lasers, that is the diode chips, can operate at very high power as it is theoretically possible. And these diodes are subsequently used for pumping ND-YAG rods, and for these lasers are used for industrial applications. Now this technique is now very well standardized, established, and this has been put for technology transfer and incubation. And I'm sure in coming few months time, this also will be done, because the party has shown already keen interest. And if we are successful in deploying these things, there will be a spur of activities using these lasers, because now the dependence on imported components will be reduced. We had a high energy laser program also. So we are developing control systems for this high energy laser program, because there is again number of laser systems to be controlled and operated with many other devices along with that. So this is a epic bus system that has been developed. Coming back to the material science activity, we had a carbon aerogel based activity that is very useful. Particularly, we had taken up it for heavy water applications, for heavy water decontamination application. Earlier, we had supplied a lot of Dixon rings, around 12,000 Dixon rings were supplied earlier, and those were operated very reliably. There were very successful results from that. Now, we had gone for a specialized structural tracking structures here, and these are 45 such modules are given to BRC for heavy water division BRC for further field trials. And we are very sure that this will give excellent results and there will be further demand. Another application that we have tried is to have a supercapacitor that is based on this carbon aerogel and this technology. This we got fabricated from a industry at Bhopal, and this is a 4.5 kilojoule with ESR as low as 5.5 milliohms. And this capacitor has been tried in a Maruti Wagon-R, and it has been replacing the battery there. And it has been tried number of times on campus, and it has operated successfully. And if industry comes in, then we will be taking it further. But we are very sure that that's why this capacitor was fabricated very specifically in that size to fit into the battery. Standard auto car. Coming to the materials again, we are having certain crystal growth facilities, and KDP crystal we were growing for many years. And this year we have grown the largest KDP crystal in the country, which is 160 by 150 by 120 mm and weighing 5.5 kg. So this is a great achievement. And these crystals will be used for making devices subsequently, because we'll cut the proper slices from this and we'll go for focal cell and other device applications from this. Incidentally, CGCRI has technology for coating this, so we'll have collaboration with them in future. And this laser beam visualizers, this is another material science application that is going on. And this has been developed. Earlier, we have gone up to around 1.5 micron. Now we have extended this range right from 350 nanometers to 2.2 micrometers. So this will be very useful in detecting beams and even power and energy measurement applications subsequently. We are into the nanoparticle generation also. So this is a automated system is prepared for preparing uniform gold nanoparticles for different applications, because these are finding applications in many various areas, and we had established a process for this with very good control on the parameters. Coming to photonics application, we are developing machine vision systems for automated inspection of various nuclear fuel components that are required. That inspection is to be done at NFC. So as you must be knowing, there are large number of components at very precise and differing, varying in size and shapes. And these need to be inspected at much faster rate, as India is progressing ahead with the fleet mode of 700 megawatt reactors. So there is a lot of demand on fuel also, and quality control is a prime in all these applications. So machine vision systems comes handy in such applications, because a person has natural limitations of his efforts, and these systems are definitely useful here. So we had ABTR top slot measurement system. Here we go up to 10 micron accuracy and 2 plugs per minute. Then these are various cobalt plug monitoring. This is a 6 plugs per minute and 10 micron accuracy. And these are very specialized punches where 6 micron resolution is required. And there are at least 6 to 20 parameters that are being measured, and automated report is generated using this. We have a fiber Bragg rating generating system here, and this we are utilizing for various industrial applications. One of this is now we are also utilizing it for temperature monitoring in nuclear reactor. This is as alternate technique to the existing one because this was another requirement from AERB. So this we had given. Apart from this, as stated earlier, last year, we are giving these fiber bracketting sensors for railway safety applications. And now Vikram Sarabhai Space Center, they had also come up with their own requirement and will be fulfilling that in months to come. So this indigenous setup for this FBG fabrication is very well utilized, and we are offering this through our incubation services also. Another application of photonics is on-core diagnoscope that we had I indicated last year also. But now this industry has come up with a nice device which is much better than what we could do because they had gone for a product design, specialized product design. And this has been extensively used. We had gone to remote places like Mandgaon and tribal areas of Sagar. I'll elaborate slightly on that subsequently. But this device has been extensively used, and as on date, around more than 5,000 samples are worked out on this. Now I'll quickly go through some of the remaining technologies, particularly computers, mechanical fabrication, and our HRD efforts, infrastructure, and some of the industry interactions. Our computer division is very active. Apart from providing all services for efficient data management, network management, they're taking up other development tasks also. So one of the tasks that has been completed is automated speed detection system and identifying the vehicles also on the campus. So it has been done using artificial and machine learning technique, and it is being used, and successfully it is operating here. Another thing is network security is very important, and a very advanced system is developed here that is for to detect and isolate network points with indicators of compromise and indicators of attack. This is very much required for a secured network system. This is a very complicated layout here. But, these are the various modules that are developed and integrated, and thus is this computer division is providing a safe and secure network for our employees. Then this is a very specialized mechanical fabrication, that is the aluminum to stainless steel diffusion welding. This is a very unique technique, and it has gone up to bond strength of 50 megapascals, and diffusion welding is done at 560 under high vacuum. So this is very important, and very specialized processes need to be developed to come to this result. And I'm sure this will find many applications in time to come. Coming to our incubation activities, as indicated last year, we have done this technology transfer under incubation with Tata Motors, and we are expecting a product on wheel in months, few months from now. So this will be successfully completed. The same technology is now, there is an interest in fish industry to have a reliable storage of fish, where earlier this ice is used, and there are many disadvantages there. But now we had a MOU with CIFT, that is the Central Institute of Fisheries Technology, and an eco-friendly system which can be economical and easily deployable will be developed. This is the first prototype that has been developed. I hope this will go on Sagar Harita ship that is operated by CIFT in near future. Another fabrication technique that is developed is low magnetic permeability TIG welding system. Specialized gas lens is developed, and with this you can go for a very precision welding here, and very smooth welding. So this is without gas lens, and this is with gas lens. The difference is clearly visible, and mu r is brought to 1.01 from 1.3. So this, of course, the advantage. And there is another ATIG welding also that has been developed. I'm sure both of these techniques will go and find applications in industry and take us for this technique. This has come up with our collaborative efforts with IGCAR, because IGCAR is expert in welding technology, and there are variety of requirements where our expertise can be used. Homi Bhabha National Institute is operating from RRCAT. We are a constituent unit of HBNI, and we had last year 8 PhDs were awarded, 6 PhD students joined, 10 MTechs awarded, and 8 TSO joined for their MTech project. A strange coincidence is there that all 6 PhD students were female students this time who joined. So we talk normally of gender equality, etc. But this is the other end of that has happened this year. Then we have conducted HBNI theme meeting. This is the life sciences theme meeting, first ever organized over the DA units, and it was a very successful. Lot of interactions took place. We had a graduation function of 22nd batch of RRCAT training school. Dr. Shashank Chaturvedi was here, and this HBNI is celebrating all other different functions. Like this time, we had a very specialized function on Bharatiya Bhasha Utsav on 11th December. This TASAR program, where we take ITI trainees for 1 year and give them on-the-job training, and in turn, they also contribute to the departmental programs. This is a very beneficial program to all the stakeholders. It is a win-win situation for trainees, RRCAT, and country as a whole, and to the industry also. So they are getting good training, and they are getting employment in many reputed organizations like this. So we had the infrastructure development also going on. I've shown very few only highlights of this. For North Gate, that is unoccupied area also, we have started occupying it, and some basic developments. We are contributing to the sports activities, and TASAR trainees, we have taken particularly ladies trainees should get hostel accommodation. With that, we have processed further. And as you know, Indore is the cleanest city of India, and RRCAT is the cleanest campus of the Indore city. And we are continuing with this tradition. And this year, our horticulture section received on this 35th annual Rose Show exhibition overall championship due to our large number of awards in different categories. We won around 15 awards in totality, and we were the overall champion, and you all experience this beautiful campus every day. And to the societal clothes, because we have dedicated this palace, Sukhnivas Palace, and converted into a light exploratorium, that is Prakash Vigyan Sangrahalaya. This was inaugurated by Dr. Anil Kakodkar on 8 July, and now we make it accessible by invitation to school students, college students, and anybody interested. So we had a public outreach activity also. We had the celebrated DAE Iconic Week, and had interactions with many academic institutions around Indore, going to very primary level schools at remote places to the elite colleges and institutes here. And we had industry interaction also during this period, and many industries have come. We had a special industry interaction session. In collaboration with IIT Indore, we had conducted a certificate course of additive manufacturing. This was an online course conducted on Saturday and Sundays, and this has been completed recently. And we had been participating in some of the important programs. There's a outreach. This oncodiagnoscope has been taken on this Lifeline Express, which is operated by Impact India Foundation. It goes to the very remote areas where normally doctors and hospital facilities are not available, and it has been utilized there. Our scientists went there and operated this. Dr. Anil Kakodkar was also witnessing the thing there. And some of our incubation activities are also going on well. This is with Dr. Cure and Care. The product is almost ready now. We are waiting for its final trial so that it will get launched online. And this is the 10 MeV LINIAC that now we have transferred it to industry for operation in industrial environment, so that once we develop it, we'll be ready to deploy it in industry. This is Microtrol Sterilization Limited, Mumbai. They have taken this LINIAC, and it is being installed at Bangalore now. It will be operated in industrial environment. So these are the other activities. We had academic MOU last year with VIT Bhopal, and Dr. Kamachi Murli was there at that time, and we signed this. We had academic MOU with DAVV Vice Chancellor Professor Renu Jain was here, and we had MOU with Oriental University also, and I'm sure with this there is a lot of increased academic interaction. We had MOU with industry, as stated earlier, with Microtrol for incubating getting experience in industrial environment. This was through incubation center, and we had MOU with Central Institute of Fisheries Technologies under ICAR. This is for developing the liquid nitrogen-based transportation system for fishes. And we had 4 MOUs that will be signed. Finally, the papers will be transferred today, just after my talk today. So I'm sure with these R&D institutes and academia and industries working together with innovative ideas, we can write success stories for Atmanirbhar Bharat. And this is the need of the hour, and we should contribute for this. This year's logo also, this Vasudhaiva Kutumbakam, that one nation, one family, and one future. It shows that we need to contribute for that. And with noble mind and dedicated efforts, we can go for that. So thus we'll be serving our logo, that is photons, serving the mankind through science and technology in line with atoms in the service of nation. We are highly specialized in the area and will keep on contributing. Thank you.
Thank you, sir, for sharing the information of last year's achievements and accomplishments of RRCAT. Now, as Dr. Nake has mentioned that now we will be having a small ceremony of technology transfer, where a few RRCAT developed technologies will be transferred to the Indian industries who have shown interest in commercializing our technologies. I'm pleased to share with you that we have with us today Mr. M. Srinivas, Director, Lokesh Machines Limited, Hyderabad; Mr. Manoj Jain, CEO, VFuse Metal for Manufacturing Private Limited, Bhopal; Mr. Hrishikesh V. Iyer, CEO of Ideas AM Systems, Mumbai; Mr. Rahul Dalal, Founder, Metal and Membrane, Rao, Indore; Mr. Dhruv Goel, CEO, Technica Fiber Technique Private Limited, New Delhi; Mr. Abhishek Bardia, Head MP Startup Center, Bhopal; and Mr. Sharup Chandra, Founder, Adrotech Group, New Delhi, who have come all the way to RRCAT for taking our technologies. Now, I would call upon Dr. C.P. Paul, Head Technology Transfer Cell and RRCAT Incubation Center, onto the stage to conduct the technology transfer ceremony. I hand over the mic to Dr. Paul for the proceedings of the technology transfer. Dr. Paul, please.
Thank you, Dr. Majumdar, for inviting me for the session. With the inauguration of the incubation centers at RRCAT along with the BRC, IGCAR, IPR, DA incubation policies, guidelines in the place, there have been many initiatives taken under the leadership at the RRCAT, and now we are seeing a visible change, not only in the perception, but also in the technology transfer and incubation activities. Today, incubation center activities includes technology development with the industries, extending the spare capacity of state-of-art infrastructure to the industries on the chargeable basis, offering certificate courses in the relevant niche areas, and there is more than threefold increase in the revenues. If you see, we are working in the area of the technology transfer, incubation agreement, incubation services, and the courses, and committed revenue. If you see the revenue now, in 2021 we had 34.4 lakhs, which is now going to be 112 lakhs plus, which shows that the people have interest and people are working all over this part of this. If we talk of the technology development partners, incubators, and clients, these includes Tata Motors, Becton Dickinson, Microtrol, Dr. Cure and Care, Research India, and Applied Optical Systems. So many things are going on. So today at this occasion, we have one technology transfer on the Agni Rakshak. We have three incubation agreement handover in terms of the in-house technology for thruster, laser additive manufacturing systems. And then we also have technology transfer document handover for the collaborative technology incubation for the circumferential TIG welding and special welding machine development, which are going to take on. Now I request Dr. S.V. Nake, Director RRCAT and the Chairman, Incubation Center RRCAT, to accompany today's chief guest and our patron, Sri K.N. Vyas, the Chairman, Atomic Energy Commission, and the Secretary, DAE, and the guest of honor, Dr. U. Kamachi Mudli, Vice Chancellor, VIT Bhopal, to the dais. Let's start the ceremony with the technology transfer of Agni Rakshak. Agni Rakshak is a Raman optical fiber-based distributed fiber sensor systems capable of detecting the temperature rise and its location with an accuracy of 3 degrees centigrade for a distance of 1 kilometer. This technology is being licensed to non-exclusive basis to Fiber Technica Fiber Tech Private Limited, New Delhi. I invite Mr. Dhruv Goyal, CEO, Technica Fiber Tech Private Limited, New Delhi, to come to the dais. I request technology developer, Dr. Om Prakash and Dr. Manoj Saxena to join him. Yes, sir. Actually, you can show this. So you can come. So you can come in the center. You can come on the center. Yes. Kamakshi, sir, you also. Yeah. As per DAE incubation policy and guidelines, the developed in-house technology is first made available through technology transfer, and subsequently industries and the startups are invited to submit expression of interest for the value addition to the technology. The parties submitted the expression of interest after seeing the lab prototype, and they shared their idea of value addition and the business plan to take the technology to the industry. The selection panel evaluates the capacity, expertise, value addition, and the business plan comprehensively, and based on that, they award the incubation on the predefined merit points. Based on the capacity available with the technology development team, the number of incubatees for the technology development is taken up and the people join as a technology development partner, or we are going to have first incubation agreement transfer on the laser additive manufacturing using directed energy deposition. It is always good to have a specific name to the technology before it goes to the public domain. Hence, the suggestion for the name of this technology was invited from the RRCAT members, and after scrutinizing the list of the suggested names, thruster is selected as the name for this particular technology. Thruster is the name of a rishi from Rigveda who was a skillful craftsman and artisan deity like Vishwakarma. He built many wonderful objects, including Indra's bolt, Brahmati's axe for divine and food ring. Thruster will be incubated with the 2 startups and 1 CNC machine giant to bring paradigm shift in Indian and global manufacturing ecosystems with the induction of indigenous thruster technology. I would like to mention here the price of the machine, which was being sold by Europe and North America as 5 crore and above. Now I call upon Mr. Rishikesh V. Iyer, a young man leading startup Ideas AM Systems, Mumbai, for the exchange of the incubation documents. His target is to cater the product in the domain of academia and R&D labs by providing a cost-effective machine, which will be ranging in the range of 50 to 100 lakhs. Now I call Mr. Manoj Jain, a man with 13 plus years experience in AM industries and CEO of a new startup, View Fuse Metal for Manufacturing Private Limited, Bhopal, to the dais for exchange of incubation agreement of the thresher. View Fuse will incubate the technology to develop a product by joining conventional and the laser source to a cost-effective solution. The target market segment is Indian industries and the national labs. Projected price of thruster will be 200 to 350 lakhs. Now I call Mr. M. Srinivas, Director, Lokesh Machine Limited, Hyderabad, a well-known name in CNC machines. Lokesh is a public limited company with its share listed in BSE and NSE. The company has annual turnover 200 plus crore with 15% export of the CNC machine in 22 countries across the globe. Lokesh will jointly develop the cluster technology by developing additive and subtractive machine and push the market to the Indian and the global market. The project cost of this machine is 150 to 250 lakhs. Technology expertise developed at RRCAT should be shared to solve the various industrial problems, and where the collaborative technology incubation comes into the picture. One of the such problem was forwarded by a MSME company from Indore to weld the solid and porous materials. The technology developed from RRCAT worked and agreed to take up the work under the collaborative incubation. Now I request Mr. Rahul Dalal, the founder of the Metal and Member Private Limited, Rao Indore, to come on the exchange for the exchange of the incubation agreement. I request Mr. Abhay Kumar, head DMTD, as a technology developer, and Mr. Praveen Agarwal as a representative incubation center RRCAT to join the stage. We have many more technology and incubation agreements in the pipeline, and we are closely working with the industries who push this technology to continue the self-reliance mission of India through Parmanu Urja Ka Samarthya Atmanirbhar Bharat. Now I hand over the stage to Dr. Shabun Majumdar back.
Thank you, Dr. Paul. As we are celebrating the 40th Foundation Day of RRCAT, we are extremely delighted to have Professor Kamachi Mudali, Vice Chancellor, Vellore Institute of Technology, Bhopal, and former Chief Executive and Chairman of Heavy Water Board with us. Although Dr. Mudali doesn't need any introduction to our DA colleagues, yet for the benefit of the audience, I would like to take the privilege to say a few words about his scholarly eminence. Dr. U. Kamachi Mudali is a globally renowned researcher and academician in the field of advanced materials and coatings, corrosion science, technology and engineering, and surface engineering. A distinguished alumnus of IIT Bombay and PSG College of Technology, Dr. Mudali served at the Indira Gandhi Center for Atomic Research, that is IGCAR, Kalpakkam, with the Department of Atomic Energy during 1984 to 2017 in various leadership positions. Between 2017 and 2020, he was Distinguished Scientist, Chairman and Chief Executive of Heavy Water Board at Mumbai, overseeing production of heavy water and specialty materials at 7 different plants located in India. After superannuation in September 2020, he became the Vice Chancellor of VIT Bhopal in March 2021, an honorary professor of practice at IIT Madras. As an outstanding researcher with 11,500 citations and H-index of 50, I-10 index of 275, Dr. Mudali has salvaged several chemical, nuclear, and allied industries on cost-saving and production-oriented corrosion-related problems. He has made pioneering contributions to high nitrogen SS alloys and weldments, titanium and zirconium alloys, bulk metallic glasses and coatings, laser and ion beam surface modifications, superhydrophobic, electrocatalytic, self-cleaning and thermal barrier coatings, biomedical alloys and coatings, etc. He has been instrumental in material selection, fabrication, and evaluation of components of first breeder reactor and associated fuel cycle plants of DAE. Dr. Mudali served as Senior Professor of Homi Bhabha National Institute at Kalpakkam, conducted academic courses, and guided and coordinated around 162 UG, PG, and PhD students from many academic institutions. He has driven successfully 21 R&D projects under industry-academia collaboration. Dr. Mudali's research interests are evident from 474 journal papers, 22 edited books, 5 patents, and 295 invited presentations. Dr. Mudali is recognized in the world's top 2% scientists from India in the field of materials and is decorated with many distinguished recognitions: Metallurgist of the Year Award from Government of India and Indian Institute of Metals, and GT Birla Gold Medal, Platinum Medal from IIM Kolkata, Tamil Nadu Scientist Award, Mascot National Award, and Lifetime Achievement Award from ECSI Bengaluru. Vasig Award, Indian Nuclear Society Medal, Distinguished Faculty Award from HBN University, AICTE, INE, Distinguished Visiting Professorship by INE, Homi Bhabha Science and Technology Award of DAE, Group Achievement Award from DAE 5 times, ONGC Excellence and Meritorious Awards in Corrosion from NAC India and NCCI, like several others. That list is very long. I will not go in detail. And Dr. Mudali is a trustee of ASM International USA and a fellow of ASM International USA. And he has very other association with very other professional bodies. And he has provided, Dr. Mudali has provided leadership and expertise as chairman to various committees. And presently, he is the Vice Chancellor of VIT Bhopal. So with this brief introduction, I invite Dr. Professor Mudali to address the audience.
Good morning. Thank you, Dr. Mazumdar, for a beautiful introduction that you gave about me. Honorable Chief Guest of the Foundation Day, 40th Foundation Day of RRCAT, Sri K.N. Vyas, Secretary, Department of Atomic Energy and Chairman, Atomic Energy Commission, Distinguished Director, Dr. Shankar Nake, RRCAT, Indore, and colleagues, Dr. Majumdar and Dr. Purushottam on the dais, former directors of RRCAT, former distinguished scientists of RRCAT, the employees, staff, the young scientists and research scholars, special invitees, ladies and gentlemen. I'm really delighted and honored to be here as the guest of honor. I want to thank Dr. Shankar Nake for giving me this invitation. The last occasion I was here on the iconic week DAE celebrations, where I was addressing about the advanced technologies made in heavy water board to the industrial and academic community here. Today, when we talk about the Foundation Day, the 40th Foundation Day of RRCAT, I'm really amazed and delighted to see the host of technologies that Dr. Shankar Nake presented for nearly about 25 minutes with wonderful technologies, the advanced technologies. And I'm sure that in this domain of laser and accelerator based technologies, RRCAT is the #1 institution in the country. There is no doubt about this. And RRCAT not only caters to the non-nuclear applications and some of the reactor applications in our department, but also to the society and the industry at large. When I see all these advanced technologies, two things come into my mind. One is the sustainability. The second thing is Industry 4.0. This is what is being globally talked today. When you talk about sustainability, all of us should remember in the year 2015, the United Nations General Assembly has passed a resolution that all member countries, 154 countries, should pursue the sustainability development goals. Some 17 goals with 269 targets, I remember, has been laid out by United Nations General Assembly. And the Prime Minister or head of the state of each country in every year during the General Assembly in the month of, I think, September, they have to give what achievement has been made on these 17 goals. If you see the address by our Honorable Prime Minister in the last, General Assembly, you would see that he has given a list of achievements that we have made, particularly on the clean energy development in the country. So when we talk about these 17 goals and 269, targets, so I was going through, because being a metallurgist by base, I was thinking about sustainability of metals, because metals are the one that is greatly, I would say, abused, not say used also, I would say abused by the community, the industrial community and the society, because we think that this is all gifted by our ancestor to us. So we have right to dig it out and use it liberally. But what is that we should remember is that it all belongs to grand generations later, and we are just abusing it for the benefit of whatever limited purpose today. So unless you pursue the sustainability, which is very, very important, that is how to make things available in a better way today for the living community, as well as what should be available for the future generation, I don't think that we can achieve all these 17 goals that has been made. And this is coming under Agenda 2030, which is the resolution that was passed by the UN General Assembly. The second thing is that we all should remember Industry 4.0. I think most of you will know that it goes on with a lot of innovative and latest technologies like sensors, automation, robotics, advanced manufacturing. And I think if you see RRCAT, the list of technologies, all of them fall into that. I think they are already in the Industry 4.0 domain. Maybe that they will do excel in Industry 5.0, which people are talking today. When you talk about Industry 4.0, where you are talking about advanced technologies, I think I should be from the academic community for the last 2 years. And I want to talk about Education 4.0, which is very important. Unless you have bright young minds coming from with better education and technology capability from the engineering institutions and scientific institutions, it is very difficult for us to pursue Industry 4.0 or the Sustainability Development Goal, whatever we talk about it. And in this regard, the recent development that is happening, I think it's everybody will know this word AI, the artificial intelligence. I would also say that the new education policy of our country, which is very well crafted and laid by the government, we talk about all superficial things. We don't talk the core of the NEP. NEP says that AI has to be used as an effective tool for education in the country. And they put 4 different arms. One is digital literacy, means everybody, those who are in the school, college, and everywhere, they should have digital literacy. Second thing is coding. They should have capability to do their own practicing, the programming, algorithm development, and so on. Third is the computational thinking. You have to do minimum experiment and maximum thinking and making it into programming, and then computationally getting the results. And last but not least, the design thinking. That is digital literacy, coding, computational thinking, and the design thinking. So these are the 4 arms of the application of AI in the NEP, and I'm sure that this will give big impact in the students' outcome or the study outcome that will be seen by the future students who will study under NEP 2020. But what is people today argue is that we have a better system, but this is the system that was instituted by Macaulay, Lord Macaulay, in 1900s, and where this education system is only focusing on something called downward infiltration theory, where the British people want to use a kind of interface between the mass and between them. There is some kind of people who are educated with English. They will look in Indian by color and then by behavior, but they will speak and they will also able to take the messages from the British people to the masses. And that is how they conceived the education system. And I'm sure all of you will agree with me that we should have a kind of education policy that will take the bright mind to advances in the engineering and technology. So that way, if you see that for achieving all these advanced technologies in the future, I'm sure that getting young, bright minds with education 4.0 is very important. And artificial intelligence today, I would tell you that in 2019, the maximum worth of business was about $1.1 billion. And it is estimated by 2030 it will be $25.9 billion. That 25 times of the business will grow in artificial intelligence, so that people are going to be more and more familiar in digital literacy, coding, and design thinking and computational thinking. I think that tomorrow that we want to have more and more technology coming like this, innovative technology coming from RRCAT. We have to attract such people, and also we have to join hands with educational institutions who will implement NEP for 2021 and also give the best education with the innovative ideas, something like from artificial intelligence to the students. And that will make, I think, the future foundation days to have more and more innovative technologies that is coming and that is available for the Indian industries to take it through the technology transfer. I'm very proud to be here today joining the foundation day, and also I am delighted to congratulate all the engineers and scientists of RRCAT for making this foundation day really worth for me to attend and come to know the host of technologies that has been made here. Thank you very much and hearty congratulations.
Thank you, sir, for your very informative talk. We know that words of wisdom are like pearls in an ocean. It will be a great pleasure for us to hear a few words from our honorable chief guest, Sri K.N. Vyas sir, Chairman, Atomic Energy Commission and Secretary, Department of Atomic Energy, to mark this special day. We are extremely honored to have him here today with us. We are very much grateful to you, sir, for sparing your valuable time for us. However, before I invite him on stage to the podium, it will be my pleasant duty to formally introduce him to today's audience. Sri K.N. Vyas is a mechanical engineering graduate of MS University Vadodara and a graduate of the 22nd batch of the prestigious Bhabha Atomic Center Research Center Training School. Joining the Department of Atomic Energy in 1979, he commenced his career with forays into nuclear reactor fuel designs. In those early days of the oncoming computer age, he managed to gain substantial skills and proficiency in computer programming and developed programs to carry out fuel performance analysis of nuclear fuels, which modeled fuel design aspects like irradiation swelling, fission, gas generation and release, pellet-clad interaction, etc. The insights gained by these studies led to the design of 7x7 cluster of BWR fuel having superior performance characteristics. Subsequently, he went on to expand his repertoire, working in various projects on fuel analysis and design for the upcoming power reactors, as well as towards design of novel fuels needed for strategic applications. He also gained expertise in thermal hydraulics and stress analysis and contributed towards analysis of critical reactor core components. As a fuel design engineer, he provided key inputs to fuel manufacturing units like Atomic Fuels Division and Nuclear Fuels Complex. As a team member in Reactor Projects Group, he has played a crucial role in the completion of strategic projects executed by Bhabha Atomic Research Center. He has played an important role in indigenization of special materials as well as several fabrication and test equipment used in fuel fabrication. His expertise was useful in evolving the design of text truncate module and associated systems planned to be installed at the ITER project, a fusion reactor under construction in France by a multinational scientific consortium. Sri K.N. Vyas is a recipient of several honors and awards, such as Indian Nuclear Society Outstanding Service Award 2011, Homi Bhabha Science and Technology Award 2006, and Dr. N. Kondal Rao Memorial Award 2017. He is a fellow of Indian National Academy of Engineering 2015. His passion for tackling technological challenges has remained undiminished with age, as evidenced by his recent work in computational fluid dynamics studies of soil flows in heat exchangers. These studies have led to the superior understanding of heat transfer enhancements, and in recognition of this excellent work carried out by him, he was awarded Master of Science by the Homi Bhabha National Institute in the year 2016. Sri K.N. Vyas is a strong team player and recognizes the importance of teamwork and collaboration in successfully implementing projects. He and his team have won several group achievement awards in the years 2007, 2008, 2012, and 2013 in the field of design and development of critical reactor system equipments, as well as successful erection and commissioning of various reactor systems. The leadership, insights, and guiding hand provided by him as Director of Bhabha Atomic Research Center since February 2016 has led to substantial progress in all aspects of basic and applied research in engineering, physical, chemical, biological, and material sciences, with a special thrust towards development of applications for societal benefits in the energy, health, food, and agricultural sectors. Sri Vyas is a chairman of the Board of Governors of Tata Memorial Center, Institute of Plasma Research, Homi Bhabha National Institute, University of Mumbai, DAE Center for Excellence in Basic Sciences, Saha Institute of Nuclear Physics, National Institute of Science Education and Research, Institute of Physics, and Harish Chandra Research Institute. Sri Vyas is the member of Management Council of Tata Institute of Fundamental Research and co-chairman in the governing body of Institute of Mathematical Sciences. He has assumed charge as Chairman, Atomic Energy Commission and Secretary of Department of Atomic Energy of September 20, 2018. With this brief introduction, I request Sri Vyas sir to please come on to the podium to address the gathering. And I request the dignitaries on dais to please take seat in the audience.
Thank you, Dr. Majumdar, for the not so brief introduction, and most of it is not really relevant for this audience here. सबसे पहले तो मैं माँ शारदा को प्रणाम करूंगा. With so many persons from academies, including Professor Amran Pal, whom I had a chance to meet just a few days back. I think this is the right thing, that the goddess of knowledge, we are bowing to her. Other dignitaries present with me, Dr. Kamachi Mudli, today's guest of honor, and I know him more as a chief executive of Heavy Water Board. Of course, his present responsibilities with VIT, Bhopal. Dr. Shankar Nakhe, who has been so very nice to have invited me. Dr. Purushottam Srivastav, and of course, Dr. Majumdar, who introduced me so very nicely. I thank and congratulate all the colleagues of RRCAT for excellent work that has been done in the past, as presented by Dr. Nakhe. I congratulate Dr. Nakhe for the same, and I congratulate all the senior members who have mentored this great institute, who are also present there. I owe to them that the tradition that they have started is continuing, and it is going to improve further. Members of industry who have taken our technology, please come back to us if you have difficulty. The idea is the technology would have matured to possibly TRL level 6 or 7. It was going to need efforts from industry to take it further so that it really becomes good. And the students who are there, who are going to be sort of taking this work still further, ladies and gentlemen, first of all, I must tell you the truth. I was having slight fever yesterday. I had about a couple of hours yesterday morning to sort of make this presentation. Usually my presentations are a little better than this, so please tolerate not such a good presentation. What I felt was a call has been given by all over the world that we have to reach net zero. Few countries have indicated a figure of 2050. A country like China has indicated 2060, and India has indicated that we'll reach net zero by 2070. This is the graph plotted by NASA about the global mean temperature. Every year you find there are fluctuations, but if you try to do some, I would say, regression analysis and really try to find an average, you find that yes, the temperature has increased, and as per United Nations, one of the reports, compared to 1880s, it has increased by about 1 to 1.1 degrees Celsius, and the call is that we have to limit it to 1.5 degrees Celsius. All of us are experiencing the vagaries of weather. Already weather was difficult to predict. If you really see Indian monsoon, the monsoon period has reduced. That is, it starts and stops practically during the old 4-month cycle or 3.5-month cycle, depending upon where you are staying. But the total rains which have occurred, total rainfall is same, but the number of days on which rains is happening has reduced. So what I'm trying to tell is, the rainfall intensity has increased. It has become random, it has become little arbitrary, and it is quite severe. So this is one of the first, I would say, feeling that we get of global warming. Yes, many locations the temperature during summers have become unabasably high. So still people are not able to correlate very precisely what has happened. But then the net effect that what we see is that the rate of temperature rise, which was in the beginning of the 20th century, it is certainly significantly higher. So we have to find out some solution. One of the important thing is we need to have electricity. This is the figure of around, this is a photograph, NASA photograph of about 2015-16, I'm not recollecting exactly. And this is the photograph about 10 years back, 2004 or 5. Yes, India is shining. We need electricity to make the cities sort of function day and night. But this is going to get coupled with increased demand of electricity. Number one, if we want to have industrialization, if we want to increase our quality of life, electricity is going to be more important. Because of farm incomes, the quality of life is not expected to go up very significantly. But in addition to that, when we go for green technology, we are thinking of switching over, not thinking, we will have to switch over sooner or later to electrical vehicles. Those vehicles may be driven by fuel cells, which will need hydrogen. Lots of industrial uses for, say, for steel production or cement. Also, a lot of carbon dioxide is getting generated. So we may need even green hydrogen that also will have to be produced ultimately by some of the methods of electrolysis or maybe some of the chemical processes. So one of the easiest thing that comes to our mind is make you can say solar parks. The largest solar park is in Rajasthan. It is being planned. It is not fully occupied. Badla solar park. It has a potential of about 2,200 megawatt spread over 5,700 hectares. And then it's just a Google map photograph of the place where some of the solar panels have been set in. And you see that it is able to give electricity at a very competitive rate. The latest, one of the cheapest one was less than 2 rupees. I think 1 rupees 99 paise or so per unit. So it's a very cheap and economic source of power. But and yes, if you consider the map of India, I will just like to bring in here this P I have written as in red. It is megawatt peak. So any I mean, all of you know that any solar panel that you are going to make, it is not going to generate any electricity in the night. Certainly during the maximum, when the solar insolation is maximum, at that time only it is going to be the peak acceleration, peak power. So in India, we have a very good, huge solar potential compared to wind. In United Kingdom or Germany or Norway, etc., wind potential is relatively high as compared to solar. But in Tamil Nadu and West Coast, in the Maharashtra region as well as Gujarat, large number of windmills, wind farms also have been put in. As was seen, about 5,700 hectares of land was needed for about 2,200 megawatt peak of solar power. This is you can say schematic prepared by Nuclear Energy Institute for a typical 1,000 megawatt installed capacity. Nuclear needs 1 mile square. Each one is a mile square. Solar needs 45 to 75 depending upon the solar insolation that is going to be there. Wind needs still higher. So this is relatively a very concentrated source of you can say the installation that one can have if one puts a nuclear power station. A typical example is Kudankulam, where we have Kudankulam 1 and 2. This is the Apple Maps photograph of this. Kudankulam 1 and 2, at least the persons who are in RRCAT would know very easily. These are the two operational power stations having 1,000 megawatt each. 3 and 4 construction has started. It has reached reasonably high level, and 5 and 6 construction has just begun. Just first pour of concrete has taken place. But if you see, this is going to be about 6,000 megawatt electric, and it is going to need about 1,000 hectares. If we compare with the solar, it is going to occupy certainly much lesser space. This is the photograph of Kudankulam. Now there is a very good site available by Adani Green Energy. They have, I would say, solar plants spread all over the country, and they have a unified control system and control center which looks after the dispatch of the electricity. So a very good, I would say, information is available from there. So I had looked it up about an year back. So it has about total installed capacity is about 3000 megawatt, and it gives very nicely the solar, power, which is the electrical power which is pumped into the grid. So I had taken some data from 9 to 15 November 2021, and you see that even though the total installed capacity is 3000 megawatt, even in the during the noon, it has not reached 3 megawatt. It is just barely crossing 2 megawatt. And otherwise, for rest of the day, you find that it is not able to really generate any power. Obviously, the sun has set, and as a result of that, there is not going to be any power pumped into the grid. I thought, is it because of November? Because it's a winter season. Obviously, solar installation is going to be less. So I looked up after about 6-8 months of time, 6 to 11 April 2022. Yes, it is still not reached 3. I do not know, some in 6 months they might have decommissioned some of the plants. I'm not very sure of it. I have not tried to clarify also, but it did become little more compared to 2.5, compared to 2 gigawatt electric. It is becoming 2.5 gigawatt electric. But at the same time, the power, when it is available, it is between 6 o'clock in the morning to about 6 o'clock in the evening. It is not, it's like that in summer we have more light, but it is not directly falling into the solar panel. So the electricity generation is not going to be so very high. And this is possibly the reason. Once again, these are my conjectures. All of you can also have an independent look at this particular thing. And you see, during this period, there is so much of fluctuation. It could be because of some cloud and so on. So all I'm trying to tell is, as you all know, that solar cannot be the base load power station, cannot give 24/7 electricity, and this is one of the proofs in this particular direction. Now, second thing is about the amount of carbon dioxide that is going to be pumped in. If you have a nuclear power station of 1000 megawatt electric capacity, and if you compare with 1000 megawatt electric coal fired, this is just an indicative figure. It may not necessarily be a 1000 megawatt plant. So this is just an indicative photograph. So this needs about 20 hectares of land. This needs about 70 hectares of land. Why so much of larger land? It needs a complete coal processing facility, coal transportation, and so on. So land that is going to be needed is going to be higher. Nuclear power station needs about 160 tons of fuel per year. This is going to need about 47 lakhs or 4.7 million tons of coal per year. This has negligible emission, while this has a significant amount of emissions. This results into about 4 tons of vitrified waste per year, while this has about, depending upon the amount of ash content in the coal, this is an indicative number, about 2.6 million tons of year of ash. So the point I'm trying to make is, thermal stations, thermal power station over a period, they will need to be discontinued if at all we have to meet net zero by 2070. And nuclear as a base load can be one of the significant contributor. Nuclear reactors in India, we have about 7 sites all over the country. The dots which are in red, they are the sites where the reactors have been already they are operational reactors, and the green sites are the fresh sites where the plans to, somewhere the construction has started, somewhere site like Jaitapur, they are still under negotiation. But for example, Gorakhpur nuclear power station construction has started. Now, how have we performed? Not very well, if you see. If you see, when it comes, there are about 32 countries which have operational reactors, 441 reactors. Largest number of reactors are in USA. When it comes to number of reactors, we have, if you see the NPCIL website or DIE website, we have about 22 reactors. We have 7th largest fleet so far as number of reactors are concerned. But when it comes to total power, sort of terawatt hours put into the grid, we are way behind. This is primarily because the nuclear reactors in India are usually about 200 220 megawatt or so. Only in about 2004 or 5 we had first 2 sets of reactor, that is Tarapur 4 and 5. After that, immediately just around that time Kudankulam also came up, but till that time all of them were 220 megawatt. So even though number of reactors are large, the number of the total power that is put into the grid is much lesser. Just compare it with Korea, it has just 2 reactors more than us. Instead of 22, it is 24. And since most of the reactors are 900 or 1000 megawatt, as a result of that, power that is put in the grid is much higher. So one of the things is going to be, NPCIL has to continue making the reactors as fast as possible in best possible way. So fairing wise, I would say, even though and what was the reason why we had just 200 or 220 megawatt reactor capacity? In that time, grid was not so stable. All the grids were not interconnected. So the way we have today in mid 70s and early 80s, the grid was relatively I would say more isolated, so it could not take 700 megawatt reactor or 500 megawatt reactor in those days. But when it comes to performance of nuclear reactors, it is quite good. More than 42 number of times the nuclear reactor has operated for more than 365 days in a year. So, and with this, there is a world record which was formed by Kaiga generating station. Now it is broken by a Canadian reactor, but in December 2018, it ran continuously at 960 continuously for 962 days. It is about 2.5 years of time, and at about 99% capacity factor, it's a very good performance. This is the photograph of Kaiga generating station. Now, just there are so many capable people, so just couple of things about nuclear reactors which you will already know. Basic thing is it is a fission chain reaction has to be set in, where the mass defect is giving the equivalence to energy 200 MeV, and as a result of that, if you it's a very huge amount of electricity. A simple carbon combustion equation gives only 4 eV compared to that 200 MeV. And yes, India started quite early, where Dr. Bhabha was elected as the president of Peaceful Uses of Atomic Energy Conference in 1955. We started quite early. Now, in nuclear reactors, the challenges which come are, number one, runaway chain reaction. This is not all that insurmountable, but what makes the design complicated is the decay heat generation. These two radioactive fission fragments which are generated, they are made just some time back. As a result of that, they are going to emit lot of radioactivity. So it is going to have number one, decay heat generation. It's going to generate heat and radioactive fission products also. So in case if core melt accident takes place, because if this particular fuel sort of gets failed, in that case, these are the two problems which are going to which are needed to be addressed. And of course, there is a problem of red waste management. Now, to give an idea, immediately after shutdown, the decay power is about 6.5% of the thermal power. So a 1000 megawatt electric operating at 30% efficiency will give about 3300 megawatt thermal. 6.5% of that it is going to be more than 200 megawatt. It's a huge amount of heat. Even the heat is not becoming zero even after 1 day. It is still 16.5 megawatt. So we have to ensure cooling, and that is what creates bigger and bigger problems for a large size reactor. This is the schematic of an evolutionary PWR, that is EPR of France, EDF. It has got double containment. Its internal diameter is about 47 meters from here to here, and it has a free volume of about 80,000 meter cube. It's a huge structure, and that is what makes everything more and more expensive. Similarly, in case if there is core melt taking place, there is a good possibility that it will melt through the reactor vessel. It will have to be collected. This is what happened in Chernobyl. There was no core catcher in Chernobyl. As a result of that, when the core melt accident took place, ultimately the radioactive fission product along with the fuel went below the ground, and it contaminated subsoil water, and a fair amount of radioactivity had spread. So you need the complete thing about melt spreading area. This has to be cooled also, and that is what once again makes the nuclear reactors more expensive and more difficult to construct. So for large size reactor, designs become very complex, and this results in both cost as well as increased cost and increased time for construction. And if you make mistakes anyway through the way it is happening in case of Flamanville plant, they had originally envisaged that the reactor will become operational sometime in the year of 2012. It is still not made operational, and it is not that France do not know how to make nuclear reactors. They already have 54 nuclear reactors which are under operation. So one of the idea which is being floated all around the world is having small modular reactors. So as it is seen, there are large number of designs already worked out, for which the power ranges from hundreds of kilowatt to about 300 megawatt or so. The idea is that you have them factory built, and ultimately it will be less complex and it may be economical. In India, Niti Aayog is trying to take up this particular activity, and then they are trying to sort of advise all of us that let us try to evaluate feasibility of design, construction and operation of these small modular reactors. So I think this is the last slide. So what I would like to conclude is DAE is a huge department. Each unit of DAE has its own capability. We saw in RRCAT, means whatever Dr. Nakhe indicated, I could understand hardly 10% of that. When he was mentioning TIG welding, etc., I could understand a little bit. But there are lots of specialization in electronics and RF cavities and pure, very high purity niobium, etc. I really do not understand much. So each and every unit has its own uniqueness. My suggestion is try to collaborate as much as you can. The way Dr. Nakhe said that there is a collaboration between RRCAT and IGCAR. Try to collaborate. In collaboration, one of the most important thing is you have to try to dissolve your ego. Even though the other person is not as knowledgeable as you are, but you have to assume that he is quite knowledgeable. Like me, the way Dr. Majumdar read out the huge biodata of mine. So you have to sort of bear with your counterpart, then only collaborations become important. My suggestion is each try to utilize the strength of the other institute, try to complement with your strength, and let us try to make India really Atmanirbhar. BRC and DA units have been forced to become Atmanirbhar because of lots of embargoes. Let us try to take it further. And I am very happy that there are industries which are showing belief in our technologies. These technologies are reasonably good. They are not as perfect as if at all you are to import a finished product. But if you invest little bit of your efforts, little bit of resources, I am sure scientists and technologists from DAE fraternity and RRCAT would come forward and make that technology even better than an imported technology. Thank you very much. Jai Hind.
Thank you, sir, for your enlightening words. Now, I request Dr. Nakke, Director RRCAT, to present a memento to the Honorable Chief Guest, Sri K.N. Vyas, sir, as a token of love and respect from all the members of RRCAT family. So this memento is basically the front side of Rajwada, and it has been developed by laser additive manufacturing technique in Dr. C.P. Paul's group. Thank you, sir. Now I request Sri Purushottam Srivastava, Director, Proton Accelerator Group, to present a memento to the Honorable Guest of Honor, Professor Kamachi Mudali. Thank you, sir. That brings us almost to the end of the ceremony. Now I request Sri Purushottam Srivastava, Director, Proton Accelerator Group, to please come on the podium for the vote of thanks.
धन्यवाद शोभन। नमस्कार। RRCAT के 40वें स्थापना दिवस के इस शुभ अवसर पर धन्यवाद प्रस्तुत करना मेरे लिए सौभाग्य है। सर्वप्रथम मैं मां शारदा को नमन एवं उनकी कृपा की याचना करता हूं, जिससे ज्ञान विज्ञान सहित हम आत्मसात कर सकें। और तत्पश्चात मैं राजा रमन्ना साहब को याद करता हूं और उनको आभार और हार्दिक धन्यवाद देता हूं, जिन्होंने इस संस्थान का प्रारंभ किया। हम इस अवसर पर परम आदरणीय श्री K.N. व्यास महोदय, अध्यक्ष परमाणु ऊर्जा आयोग एवं सचिव परमाणु ऊर्जा विभाग, भारत सरकार के अत्यंत आभारी हैं, जिन्होंने इस अवसर पर उपस्थित होकर इस समारोह की शोभा बढ़ाने एवं हमें प्रेरक भाषण के साथ प्रबुद्ध करने और सभी को प्रेरित करने के लिए आपका कोटि कोटि धन्यवाद सर। हम आपके सुझाव एवं सभी मार्गदर्शन पर अवश्य अमल करेंगे और विशेषकर आपने जो रोल ऑफ न्यूक्लियर पावर टू मीट नेट जीरो बाय 2070 इस पर जो एनलाइटनमेंट दिया है, वो हम आपके आभारी हैं उसके लिए। डॉक्टर यू कामाची मुदली, वाइस चांसलर VIT भोपाल एवं अध्यक्ष, पूर्व अध्यक्ष एवं मुख्य कार्यकारी अधिकारी हेवी वाटर बोर्ड के प्रति कृतज्ञता करते हुए हम अत्यंत हर्षित हैं। आपका ज्ञानवर्धक संबोधन एवं मार्गदर्शन के लिए बहुत धन्यवाद। मैं डॉक्टर SV नाखे, निदेशक RRCAT को धन्यवाद देना चाहता हूं, जिन्होंने इस आयोजन हेतु संबंधित हम सभी का मार्गदर्शन किया। हम आभारी हैं पूर्व निदेशक महोदय डॉक्टर PD गुप्ता, डॉक्टर PK गुप्ता, श्री जोशी जी, जिन्होंने इस कार्यक्रम में उपस्थित होकर हमारा उत्साहवर्धन किया। साथ ही पूर्व ग्रुप डायरेक्टर्स अनिल रावत जी एंड कुश साहब, उनका भी हम आभार प्रकट करते हैं। हम इस समारोह की शोभा बढ़ाने के लिए सभी आमंत्रित गणमान्य अतिथियों के भी आभारी हैं। विभिन्न विश्वविद्यालयों के माननीय वाइस चांसलर्स, इंस्टीट्यूट के डायरेक्टर्स एवं इंडस्ट्री से पधारे डायरेक्टर एवं चीफ एग्जीक्यूटिव ऑफिसर्स, आप सभी को मैं कोटिशत धन्यवाद देना चाहता हूं। साथ ही प्रेस से आमंत्रित सभी अतिथिगण, आपका अत्यंत ही आभार प्रकट करता हूं। इस कार्यक्रम के आयोजन में सभी समूह निदेशकों एवं प्रभाग एवं अनुभाग के प्रमुख, वरिष्ठ वैज्ञानिक एंड टेक्नोक्रेट्स एवं आयोजन समिति के सदस्यों का हम धन्यवाद प्रकट करते हैं। प्रशासन लेखा के सभी साथियों, निदेशक कार्यालय, सभी वर्ग निदेशक कार्यालय, निर्माण एवं सेवा प्रभाग, CISF सुरक्षा, अतिथि गृह, अग्नि और सुरक्षा के सहयोगों को भी उनकी सेवा हेतु हम धन्यवाद प्रस्तुत करते हैं। विभिन्न व्यवस्थाओं और सहायता के लिए सिस्टम ऑडियो विजुअल सपोर्ट सेल, जिन्होंने यहाँ इस कार्यक्रम को सफल बनाया, उनका धन्यवाद है। ऑनलाइन सभी जो उपस्थित हैं, उन्हीं अतिथियों एवं साथियों को इस कार्यक्रम को सफल बनाने हेतु मैं अत्यंत ही आभारी हूं एवं धन्यवाद प्रस्तुत करता हूं। धन्यवाद। नमस्कार।
Thank you, sir. Now I request you to kindly, all of you to kindly stand up for the national anthem. I request Dr. Suparna Pal to please.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता, पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल बंग, विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा, तब शुभ नामे जागे तब शुभ आशीष मागे, गाहे तब जय गाथा, जनगण मंगलदायक जय हे भारत भाग्य धाता, जय हे जय हे जय हे जय 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 हे।
So I request all the dignitaries to please join for refreshments outside this hall.